All right, Bill, are you ready to get started?
Sure.
Perfect. All right, everyone. Thank you so much for joining us for today's HMSC research seminar. My name is Cinnamon Moffett, and I am the Research Program Manager at Oregon State University's Hatfield Marine Science Center in Newport, Oregon, and I will be your host for today's talk. We are using a Zoom platform. We have your mics, camera, and screen shares turned off currently. We ask that you keep them that way for the duration of this talk to help us navigate. But please ask lots and lots of questions. Use the chat box that you can find either at the bottom or top of your screen. If you click the little chat icon, a pop-up box will open and you can put in questions at any time, and we will be able to answer them at the end of today's talk. Also wanted to let folks know that we are recording today's event. It will be put up in our past seminar page, which I am putting the link to that in the chat right now. And if you go there in a couple of days, you'll be able to see this event again, and feel free to share it with others. If you use that page a lot, please know that some of the links are broken at this time. We have lost our connection to Adobe Connect, which was how we recorded some of those. And it's taking me about 24 hours to load the new links up. So we've re-recorded about 50 of those seminars. So if you find a broken link, be patient, it should be up soon. If you are taking today's seminar for credit, Michael Banks is online and he will help moderate any questions in the chat box. So if you have anything for him, feel free to put it into the chat. And last announcements are what's coming next. So next week, same place, same time on November 19th, we'll have Jess Hoff, a postdoc at Oregon State University, talking about marine protected areas in a dynamic and changing world. So hopefully you'll be able to join us for that seminar as well. That evening, we're actually going to do a Science on Tap about the safety features of the new vertical evacuation building at Hatfield Marine Science Center. So if that's of interest to you and you want to see all sorts of cool then and now kind of photos, join us at 6 o'clock that evening. If you need the links to any of those events, you can just Google or use whatever platform you use to get to HMSC's homepage, scroll to the bottom, and there's a calendar of events there. But for today, our speaker is Bill Chadwick, one of our own. Bill got his BA in geology from Colorado College and then took a job with USGS at Mount St. Helens before going to graduate school in UC Santa Barbara, where he got his PhD in geology. Bill next did a postdoc with USGS studying the Galapagos volcanoes before he was hired with OSU's CIMRS. And he has been working with OSU CIMRS and NOAA PMEL for the last 30 years with the Vents in Earth-Ocean Interactions program at Hatfield. He was a director of that program from 2013 to 2019. He is now formally retired, so sad, from full-time work with NOAA and PMEL, and he retired in 2019, but now he is courtesy faculty with OSU CIMRS and HMSC, and is very engaged and active in research with the Axial Seamount, which is what he's going to share with us today. So Bill, take it away.
Okay, thanks, Cinnamon. So for those of you that might not know, the most active volcano in the Pacific Northwest is actually not on land. It's under the ocean offshore Oregon. Axial Seamount has had 3 eruptions in the last 22 years, and we know that it's building up for another one. It's located about 270 miles west of Astoria on the Juan de Fuca Ridge, which is a tectonic spreading center where 2 plates are spreading apart. Its summit is at 1,400 meters depth, which is about 3/4 of a mile deep, and it stands about 1,000 meters or 3,300 feet above the surrounding seafloor. Because it's so active, it's an ideal place to monitor and to learn more about how volcanoes work. So I'm going to show today how we're using real-time data from the Ocean Observatories Initiative cabled observatory to attempt to forecast the timing of the next eruption. And these same observations tell us a lot about the inner workings of the volcano and show that the magma supply rate has varied over both short and long time periods. So the big picture goal here is to use Axial as a natural laboratory to improve our ability to forecast eruptions, to better understand how eruptions are triggered, which hopefully we can apply to more dangerous volcanoes on land. So let's see if I can move forward here. I'm having trouble advancing the slide. Let's see. There we go. Okay, so as we all know, 2020 has been a very unusual year, and that applies to marine science as well. So first, I'm going to describe the many ways that this year affected an expedition we had planned, had scheduled to go out to Axial Seamount. Then I'll talk about the methods we use to monitor Axial and how we use that data to make forecasts. Then I'll talk about our latest view of what the current forecast window, eruption forecast window is. And finally, I'll discuss the changes we've seen in the magma supply rate over time and what we think that means. All right, so COVID-19 has impacted us all and certainly impacted a cruise we had planned to go out to Axial this past summer. So the cruise was originally scheduled on the research vessel Ravel in August 2020. But on March 13th, UNOLS, which is the organization that organizes the U.S. academic fleet, suspended all seagoing operations indefinitely. So all of a sudden we didn't know whether we were going to go or not. At that time, Ravel was in the shipyard getting work done, and COVID made that work get delayed. And so it soon became evident that Ravel wasn't going to be able to do the work that it was scheduled to do in the Northeast Pacific. But coincidentally, the research vessel Thompson, which is the University of Washington ship, was working around Fiji, and when COVID started, they got recalled back to Seattle, and so their schedule that they had in the Southwest Pacific got scrapped. At the end of March, UNOLS extended the stand down to July 1st, with the possibility of operations resuming after that date, but there was still a lot of uncertainty for a while. Then UNOLS and the National Science Foundation started rebuilding ship schedules, assuming a July 1st start date. And these were based on risk evaluations of various projects and the scientific priority. So by mid to late April, our cruise was tentatively rescheduled on the Thompson for September 2020. So essentially the Thompson took all the projects that had been scheduled on Ravel in the Northeast Pacific since they were back in the neighborhood. And around the same time, UNOLS issued guidelines on COVID-19 risk assessments and all the factors to be considered, and what were low risk cruises or high risk cruises and how to make decisions about that. So those included the risk reduction measures included minimizing the science party size. So on a typical cruise to Axial Seamount, we maybe would have usually brought about 20 scientists at sea, and this year we had 10 instead. Also, cruises that didn't go far from port, within a few days of port, were determined to be lower risk. So if anything happened at sea, you could come back quickly. And there have been no use of foreign ports since COVID began that I know of. The main part was for everybody in the science party, before getting on the ship, we had to go through a 14-day pre-cruise strict quarantine. So that effectively meant not leaving your home for 2 weeks. So here I am getting some exercise in my garage. It also meant no going to the grocery store. Basically, you couldn't leave your house. And we had COVID testing arranged by the University of Washington before, at the beginning and end of that quarantine. So you had to get 2 negative tests before getting on the ship. And for people, anybody who wasn't local to Newport, where the ship was departing from, any public travel would have to be done before a 14-day quarantine. So that had significant consequences for some of our colleagues that were that would have come from the East Coast or even on the West Coast that could not participate with these constraints, unfortunately. But the National Science Foundation also provided an increased satellite bandwidth from the ship. So we had enhanced ship-to-shore communication, so that partly offset that and allowed people on shore to participate on the cruise from shore. So here's the Thompson tied up in Newport at the Mach P dock. So essentially, once we got on the ship, we were sort of in our own little bubble, but there were still some COVID-related risk measures that we had to go through on the ship. Everybody on board had to take their temperature every day and record it. Also in the galley, everybody wore masks and used hand sanitizer going through the food line. And in the mess where normally there's 6 people to a table, they limited it to 2 people per table, and they encouraged people to kind of spread out in other areas of the ship to eat their meals. So besides those measures, once we left port, it actually felt pretty normal, at least for a while. We had the remotely operated vehicle Jason on board and the autonomous underwater vehicle Sentry, and we were making dives with both vehicles. But of course, this was 2020 after all, and so there was still more weirdness in store for us. Around Labor Day, I'm sure you all know there were horrendous fires in Oregon and fed by really strong easterly winds, which amazingly blew all that smoke an incredible distance offshore. So here's a satellite view where we were working near that red dot out at Axial Seamount. So this is a view from September 9th. Initially, all the smoke was blowing to the west, but south of us. But over the next few days, here's the 10th, here's the 11th, the winds were shifting a bit, and pretty soon we were in the thick of all the smoke. 270 miles offshore, which just seemed incredible. So we could smell the smoke out at Axial Seamount. It kind of seemed like fog, but not quite like fog. You know, the sunsets were crazy red for several days. So here's the view on the 12th. After a few days, a big low from the south started moving northwards up along the coast, and that the winds shifted and that moved all the smoke out of the area. But this being 2020, it also brought a big, powerful low right to us. And this says 28 knots, but it was more like 40 knots for several days out at Axial Seamount when we couldn't dive with the vehicles, and got a pretty exciting ride. So in addition, another part of having those strong easterly winds for so long were all kinds of land birds got blown out to sea, and a few found their way to the ship, including at least one goldfinch, which I've never seen before. And another thing I've never seen before is an owl came out to the ship and hung out with us for about a week. So here it is hanging out on the rescue boat. And so we figured out that this was a short-eared owl, and started reading about it on the Cornell All About Birds website. And to my amazement, one of their cool facts is that short-eared owls can travel long distances over vast expanses of ocean. Witnesses have reported seeing these owls descending on ships hundreds of miles from land. So that was a big surprise. So at first we were really worried about this owl, but it soon became evident that it was perfectly happy. It had kind of roosted on this mast above the bow, and apparently they can hunt and eat on the wing. And so he was happily munching away on seabirds and using the ship as a mobile hunting platform. And he rode the ship all the way back to shore with us. And the morning we were offshore Newport on our way back, he disappeared. So apparently he got a free ride home. So that was just one of the many ways that the 2020 cruise to Axial Seamount was unusual. And so now I'm going to turn to describing how we monitor Axial Seamount and what data we use to try to forecast eruptions. And during that cruise, we did lots of related work, but for the rest of the talk, I'm just going to be talking about the data from the cabled observatory. So I won't really be talking about what we did at sea. In general, the techniques used to monitor volcanoes are varied, but I'm going to be talking specifically about ground deformation monitoring, which is looking at how the ground or the surface of a volcano moves in response to magma movements underground. So we can use these movements of the volcano surface and the changes of the shape of the volcano to give clues as to what's happening underground where we can't see. So in general, at volcanoes like Axial Seamount, which is a basaltic shield volcano with a summit caldera, kind of like the volcanoes in Hawaii, there's a reservoir of magma that gets fed from below. And as magma accumulates, the pressure builds in that reservoir, and it actually pushes up the surface of the volcano, and the whole thing inflates like a balloon between eruptions. And then during eruptions, the opposite happens, that magma is removed from that shallow reservoir to erupt at the surface, and the surface above that reservoir deflates or subsides. And at times, volcanoes can be in a pattern where this pattern's fairly repeatable. So here's a couple of examples. The top from Krafla in Iceland and the bottom from Kilauea in Hawaii, where these are upward, up and down motions of the ground above the volcano of about 1 meter. And so between eruptions or intrusions, it's gradually going up. And then during the eruption or intrusion, it drops down. And this is repeated. And if it's a very repeatable pattern, then you can see that this data can be used to forecast when the next one might occur. So that's the idea. On land, these kinds of measurements are made with precision GPS instruments, or shown here, or leveling, tilt meters, or satellite radar measurements. Most of those don't work underwater. So instead, we have used very precise pressure measurements that we put on the seafloor. And the way this works is that if there's inflation or the seafloor rises, then this instrument measures a little less pressure because there's basically less height of the ocean above it. And similarly, if there's deflation and the seafloor drops, then the instrument measures a little more pressure because there's a little bigger height of ocean. And these things are so precise, they can measure the equivalent height change of about a centimeter. And so we're taking advantage of the Ocean Observatory's initiative Cabled Array, which has fiber optic cables going from shore, or one cable all the way out to Axial Seamount. This was installed and became online in 2014. And they're at the summit of Axial. At the end of the cable, there's a whole bunch of monitoring instruments plugged into the cable that are sending data back to shore in real time. And that includes 4 of these bottom pressure recorders that look like this, or BPRs. So I'll be showing a lot of data from these. So here's the long-term record of inflation and deflation from the center of the caldera at Axial Seamount. So in this plot on the y-axis is a change in seafloor elevation. So we've converted the pressure signal to depth, or depth change. So this is in meters. And this is going back 22 years from all the way to 1997 to the present. So the blue is this record of depth change. The OOI, the cabled observatory, has only been around since 2014. So all the data before that is from battery powered pressure recorders that we would go out and put down, then leave down for a year or two, come back, recover, get the data. So we didn't have any real-time data, but we were able to assemble a long-term record of what was happening. And then since the OOI came online, then we've been able to link up the two, and now we have real-time data. So anyway, I want you to notice 3 things about this plot. First, you can see the 3 eruptions that have happened, one in 1998, one in 2011, and one in 2015. During each, the seafloor dropped between 2.5 to 3.5 meters over a short period of time. And then in between, it reinflated. So, the second thing you should note is that indeed this pattern appears to be fairly repeatable at Axial Seamount, although not exactly. So you'll notice that the amount that it inflated before the start of the 2015 eruption was about 30 centimeters higher than in 2011. Still, that's pretty close. And so this is a pattern that is still useful for forecasting. And the last thing to note is that between these eruptions and throughout, really, the rate of inflation has varied quite a lot. So in other words, the slope of this line is varying quite a bit, and it's a lot steeper between these 2 eruptions than before. So we'll talk about that some more in a bit. So just zooming in on the part of that same record since 2010. Again, here's the time that the OOI data has been streaming. So we were able to forecast the 2015 eruption successfully. Of course, back then we didn't have the OOI data yet. So this is what it looked like. We had just gotten a BPR back in the summer of 2013. So this is all the data we had to look at. But in the summer of 2014, we got another piece of information that showed us that Axial had inflated up to about that level. And so it was, that showed us that about the same rate of inflation had been continuing. And that was putting us pretty close to this 2011 inflation threshold. So at that time, we stated that we forecast the Axial to erupt sometime during 2015. So that was our eruption forecast window. And indeed, that's basically what happened. So that was that forecasting was done really without the aid of the OOI data because it hadn't really, we couldn't connect it, even though it had just started flowing, we couldn't connect it with the previous record quite yet, but now we can. And now we have the this data coming in continuously, and so we can see changes more quickly. And so now what we're doing this time is we're trying various ways to extrapolate the rate of inflation that we see with this real-time data to make forecast windows for the next eruption. And you can see we're almost back up at that 2011 inflation threshold, but for several reasons that I'll describe in a bit, it doesn't look like we're very close to the next eruption. And so I'm thinking that the next inflation threshold is going to be higher than the 2015 eruption, kind of like this one was higher than the previous one. So we still got a ways to go. All right, so when will it erupt? So just for perspective, volcano eruption prediction is a tricky business in general. Each volcano is different. They each have a different personality, which can change from eruption to eruption. Magma supply is often intermittent. Local conditions make it so that they don't repeat the same behavior necessarily. So most forecasts are short-term, just hours to days before an event, and often after magma has already started moving towards the surface. So at Axial Seamount, though, this inflation predictable pattern makes it a great natural laboratory for experimenting with forecasting techniques, especially with long-term forecasts months to years in advance. And it's a place where there's not much downside risk of trying it because we don't have to worry about false alarms and freaking people out who are living around the volcano. Okay, so I'm gonna describe how we're using the OOI data to try out a few different forecasting methods. So the first method we developed was using data from one of the OOI BPRs and using the average inflation rate from the previous 3 months. Okay, so how this works is in the upper left here is a plot of some of the BPR data from Axial over a period of 3 months. So on the y-axis, this is depth in meters. So between these two numbers is 5 centimeters equivalent. And so the red squiggly line is the pressure data converted to depth with a predicted tide subtracted. So, we're trying to get at just the part of the signal that's the seafloor moving, but there's still some noise in here. So part of that noise is the tidal residuals, the part of the tide prediction model that isn't quite right. So these up and downs are just part of the tides that we're not able to take out fully. And so what we do is we take an average each day. Those are these open circles in various colors. And then we average through that over the 3 months in purple to get an average uplift rate, in this case, 24 centimeters per year. And then we look at where we are in the overall data. We extrapolate that rate into the future, figure out when we're going to cross this 2015 threshold depth, and also a threshold, hypothesized threshold depth that's higher. And then we keep track of those dates because as the inflation rate varies, these dates move around, and that's what's shown in the upper right here in this histogram. So the different colors show when these different forecast dates were determined. So we're starting right after the 2015 eruption. So the forecasts back in 2015 are all in purple. Those in 2016 are in blue, 2017 in green, 2018 in yellow, 2019 in orange, 2020 in red. So you can kind of see there's been a progression of the forecast dates moving forward in time. And that relates to how initially, right after the eruption, the inflation rate was higher. So that if you extrapolated dates were more in the earlier dates. As it kind of flattened out, those forecast dates moved to between 2020 and 2022. And now it's slowed a bit more. So now we're kind of between 2022 and 2024. And this lower right plot is another way of showing the same thing. So on the right, on the y-axis is the predicted date inflation will reach the 2015 threshold. So that's these blue dots versus the date the forecast was made. So again, in the early days here, the forecast dates were closer, like 2018. With time, they've gradually gotten forward in time, and all these bumps are short-term variations in the inflation rate, little slowdowns in inflation rate that push the dates forward temporarily, and then they came back. So overall, this looked okay, but there was kind of a lot of noise. The dates moving around, not a real consistent answer. So the next thing we did was looked for ways of reducing the noise in the pressure sensor data. So in general, in these pressure signals, there's these four components we can think about. So first there's the geophysical signal. So that's the signal we're interested in. That's the seafloor going up or down. So we want to keep that and reduce these other ones as much as possible, which are other sources of noise. So the first is drift, so that these sensors drift with time. And I'm not going to talk about how we deal with that, but basically we have methods to constrain the drift and remove it pretty effectively. So that's not a big problem. The tidal signal we talked about a little bit. We remove a predicted tide, but it doesn't get all of the tidal noise. So we're left with plus or minus a few centimeters of tidal residuals. And then this last part is called barotropic noise. And this is basically due to weather. So this is basically equivalent to, when there's a hurricane impacting a shoreline, they talk about storm surge, which is basically the winds pushing the ocean and piling it up along the shore. And the same thing happens in the open ocean, except not as high, but basically the wind and the weather is pushing the surface of the ocean around, and it piles up in some areas. And so that affects the pressure that we measure at the seafloor. So you can see those last two signals in these BPR records. So again, in the upper right here, these are both 3-month records on the same time interval. The top one, the top one is the BPR located at the center of the caldera. The one below it is the BPR located on the eastern rim of the caldera. So both of them are seeing these tidal residuals, plus or minus a few centimeters. And that's this high frequency noise. And the barotropic noise is this longer wavelength up and down over days and weeks. And you can see by comparing these two records that both the tidal residuals and the barotropic noise are very similar between the sites, because it's a long wavelength signal and these are only 4 kilometers apart. But they're measuring different amounts of uplift. For example, this one's measuring 12.2 centimeters per year, this one only 2.2. So because of this difference, we can subtract one from the other, and that effectively removes all these common sources of noise, the tidal residuals and the barotropic noise, but preserves the difference in the uplift signal, the geophysical signal that we're after. And here's what we're left with. So as you can see, it's a lot cleaner signal, doesn't include all this noise. The noise level now is plus or minus half a centimeter, and we're left with a more clean view of the geophysical signal. So for the rest of the talk, I'll just be talking about using this BPR difference data. So we adapted this same forecasting method to using this this differential BPR data instead of just from one instrument. We used the difference between those two instruments. And at first we tried averaging just over 1 month to see, with this cleaner data, could we average over a shorter amount of time? But really, it was just too noisy to do that. So even with the cleaner signal, it's still varying so much over that time scale that it's a bit noisy, or noisier than we'd like. So then we tried over 3 months instead, so this whole window instead of just the beginning. And that was better. It seemed to reduce the noise. So we lengthened it further. And this is now our favorite method. So we're averaging over 6 months using the differential BPR data. And so if we're averaging over longer, then it's less variable, basically. So so what we're seeing in this histogram is kind of what we'd expect is when we're averaging over this whole time period. It was pretty consistent forecast dates between 2020 and 2022. That's what we're seeing here. But then in May 2019, there was this major slowdown in inflation rate that we're going to talk about more. And all the forecasts since then have been in this other histogram bunch between 2022 and 2024. And then in the lower right, you can kind of see, so now we've reduced all these bumps in this curve because we're averaging over longer periods of time. We still have these little bumps, which are times when there are little deflation events that are short term. So they temporarily move the dates forward and then they move back. So we're going to talk a little bit more about those. And then there's this big slowdown in May 2019 that lasts a while. And then when it comes back, the dates are a little further in the future than they were before because the rate is decreased. So that's our current view. So just to summarize that forecasting. So in early 2019, before we could really see the effect of this May 2019 decrease in the inflation rate, it looked like our forecast window was between 2020 and 2022. By late 2019, we could see that there had been this slowdown, but we didn't really know how long it was going to last. So we lengthened the forecast window to 2024. But by the mid 2020, we could see that indeed this was the new normal. It was lasting. And so we've moved the forecast window up to between 2022 and 2025 now. And of course, the rate of inflation could change again. So this is, stay tuned to see what will happen. But that's our current view. And this is consistent with the current state of the seismicity at Axial. And all the earthquake data I'll be showing is from William Wilcock at University of Washington, who's working with the OOI seismic data. So this is a plot from a paper he published with others in 2016, right after the 2015 eruption. So this is a number of earthquakes per day leading up to the 2015 eruption. So, and we're starting right as the OOI cabled observatory was turned on. So at first there were hundreds of earthquakes per day, and then within a month, sometimes it was over 1,000 earthquakes per day. A few months after that, it was sometimes more than 2,000 earthquakes per day. And then a few months after that, it was most of the time thousands of earthquakes per day. Then on the day of the eruption, it shot up to 9,000 earthquakes. And after the eruption, the number of earthquakes quickly declined down to this background level of about 10 per day. So if we look at a wider basically what's happened since the 2015 eruption till now, with the same kind of plot. Now we're just plotting between 0 and 300 earthquakes per day. So here's that background level. Here's all the high seismicity leading up to the eruption. It drops down to background, just 10 or so earthquakes per day. That lasted until the beginning of 2018. And then it slowly started to ramp up again to, between 50 and 200, sometimes more earthquakes per day. And it's been at about that level, kind of variable, but nowhere near the thousands of earthquakes per day. So that's another piece of information that tells us that it makes sense that we're still a few years away from the next eruption. Okay, so now we're gonna talk some more about, we're going to look more closely at the times when the rate of inflation has changed and the links between inflation and seismicity and what this might mean about the magma supply to axial seamount. So here's that same plot, but we're of the earthquakes per day in black, the black histogram. I've overlaid the differential BPR record in blue with the scale on the right. We're zoomed in now from 2017 to the beginning of 2020. And so you might notice that in the differential BPR curve, it's inflating most of the time, but periodically there's these little step backs, these short-term deflation events that are like steps. And so we've identified at least 8 of these, and we've marked them here by these red vertical lines. And on this plot, you can also maybe see that after each one of these short-term deflation events, the number of earthquakes drops back down for a time. So particularly after the beginning of 2018, when the number of earthquakes is higher, here's a deflation event. The earthquakes are quiet for a bit. Here's another one, seismicity drops back down, another one, drop down. Here's the big slowdown, a long period of low seismicity. And these gray bars are periods when there's no seismic data available. So these are data gaps in the seismic record. So it's easier to see this if we zoom in on one or a couple of these events. So we're going to look in more detail at this June 2018 event. So on the left is the differential BPR data. So we're inflating here. Suddenly it turns around and starts deflating. It deflates 2.7 centimeters over 18 days. So I forgot to say that all of these are between 1 and 3 centimeters of deflation over 1 to 3 weeks. So this is typical. And then it stops, it starts reinflating. And so I've got 3 red lines on here, the beginning of the deflation, the end of the deflation, and then the time when it's gotten back to its previous level of inflation. And this is over 3 months. So here's the same 3-month period, but now looking at the seismic data. So again, earthquakes per day, we're somewhere between 50 and 200 per day. This deflation event starts, all of a sudden the seismicity drops to background, and it doesn't pick back up until we're back reinflated to about the same level. So what we think this means is that the supply of magma to the shallow reservoir gets temporarily cut off during these deflation events. And the actual deflation is probably due to viscoelastic relaxation in the rocks surrounding the magma reservoir. And this same process reduces the stress that drives the seismicity. So when the inflation resumes, you have to pump the stress back up to its previous level before the seismicity resumes. So here's a cartoon of what all that means. So here's the seafloor. The shallow crust is elastic. That means it's cold and rigid. There's this magma reservoir at under the summit of Axial Seamount that's about 1 to 2 kilometers deep. It's fed from magma from below, and it's surrounded, and especially below it is a viscoelastic region. So what that means is that it's hot, it's a little bit gooey, it's mostly solid, but there's some melt in there too, so it's kind of mushy. And so while magma is being supplied to this chamber, the pressure is rising in the chamber, it's pushing upward, it's causing the inflation of the seafloor, and all that stress is generating earthquakes. But during these short-term deflation events, the supply stops, and this viscoelastic region allows magma to kind of ooze back out through porous flow. There's what's called a viscoelastic relaxation. So the pressure decreases, we get subsidence, and the stress that's driving the earthquakes goes away during that time period. So that's what we think is going on during these short-term interruptions. And so let's take a look at this May 2019 event. So it's similar to the last one. It's inflating. It deflates by 2.4 centimeters over 16 days, but then it's different. Instead of reinflating right away, it pauses, and it's not inflating or deflating. And the seismicity is similar. The number of earthquakes drops off when the deflation starts, and then it's quiet throughout this thing. So again, we're looking at 3 months. If we expand it to 6 months, same event. Here's the deflation. Here's 2 months of where it's just flat, and then it gradually starts inflating again. And it's a little bit harder to see the seismic story because there's some data gaps here, but it's basically the same as before, where the seismicity doesn't pick up until it's at least partially reinflated. So this is probably the same story, except that the magma supply is cut off here. We get this viscoelastic relaxation. Here, apparently the supply is trying to start back up again, but it's at a low rate. So it's just counterbalancing the viscous effect, and it slowly increases so that then it starts reinflating. But what's different about this event is that there's a really substantial change in the long-term inflation rate before and after. So here's a longer-term record from the 2015 eruption to the present of this differential BPR data. And these arrows show all the short-term deflation events or changes in rates that are in the record. So, and if we take the average inflation rate of each time period between these things, the rate changes slightly between each event, but in general, we were just looking at this May 2019 event. All of these before then, it was somewhere between 20 and 30 centimeters per year. Then there's this 2-month flat period, and then thereafter it's quite a bit lower by at least half. So something major happened there. So what's going on in the big picture? So if we zoom back out to our full monitoring record going back 22 years, and we noted at the beginning that there were kind of changes in inflation rate all along. But if we look at the pattern of these, between 2000 and 2010, it was about 15 centimeters a year of the inflation rate. Then in the months leading up to the 2011 eruption, it at least doubled to about 34 centimeters a year. Then between the 2011 and 2015 eruptions, it doubled again to 67 centimeters a year on average. But then since the 2015 eruption, the rates have been going back down. For the first 2 years, it's about 51 centimeters a year. The next 2 years, it's about 34. And then in the last few months, it's been down to about 13. So the inflation rates, reflect the long-term magma supply rate. So if we envision what that might look like, this is just a kind of a cartoon. What this implies is that, maybe this is some background level, but that there was a surge in the magma supply rate centered around these two eruptions, and explains why the inflation rate was so high, why these two were so close together in time. But then since then, the magma supply has been waning, and my working hypothesis is that all these short-term interruptions are a consequence or a reflection of that waning supply rate. So just to summarize the story, we've now reinflated about 85% of the level when the 2015 eruption started, but I'm anticipating that the next threshold will be higher, so we're going to have to get a bit higher than that. So our current forecast window is between 2022 and 2025, but again, that could change if the inflation rate changes again. So, and using this differential BPR data since the 2015 eruption, we've seen repeated short-term deflation events associated with changes in the inflation rate and a simultaneous drop-off in seismicity. And so these interruptions may be a consequence of a waning magma supply following an apparent surge that led to the 2011 and 2015 eruptions. And finally, I just want to acknowledge a bunch of my colleagues that have worked with me on this data and axial seamount in general over the years. Scott Nooner at University of North Carolina at Wilmington, Dave Kress, Dave Clegg, Jenny Padawan at Ambari down in Monterey, William Wilcock at the University of Washington, and HMSC colleagues from OSU CIMRS and NOAA PMEL, including Jeff Beeson, Andy Lau, Brian Kahn, Susan Murley, Tamara Baumberger, Andrew Bobbitt, Bob Embley, and Chris Fox, and the OOI cabled array team at the University of Washington that provides this great data we're using, including Deb Kelly and Dana Manilang, and also to National Science Foundation for funding this research. And I'll just end with some links to some information on the web. So there's displays of this real-time BBR data here, real-time seismic data here. You can get data from the OOI cabled array here, and we have a blog from our last cruise here. So that's it. Thanks, everybody.
That's an amazing story, and it's just so great to see such a long data set. It just doesn't happen all that, and so we can really work with that. We're getting lots of questions, and so for folks that are online, please keep them coming into the chat. I'll work through them as quickly as we can, but if we can't get to them all, please note that you can either reach out to Bill directly when we get done, or rewatch the video here in a little while. Maybe those questions will be answered, but I'll start to work through them. The first one for you, Bill, is just what is the impact of these eruptions on shore? Do we see these eruptions in any way in our coastal communities?
Short answer is no. Axial Seamount's pretty far offshore. 270 miles, and it's deep, 1,500 meters or so. So there's no real effect at the surface of the ocean. It's far enough from the coast that, there's no effect on the shore. We don't think that eruptions out on the ridge affect the subduction zone, for example. What happens at the volcano doesn't affect our earthquake risk. We don't think. They're just too far away. So it's really out there in its own world. If you were out there on a ship and it was erupting underneath you, you could you probably wouldn't notice unless you dangled something down like a hydrophone or some temperature sensors, but you'd have to get pretty deep to see the effects of it.
And what is the spread of the magma with one of those eruptions around the caldera? Like how far out does it go?
How far does it go?
Yeah.
The eruptions we've seen start in the caldera, and there's Axial has a rift zone that goes to the north and one to the south, and the magma travels underground along the rift zone for quite a long ways, like 30 to 50 kilometers, and can erupt all along the rift zone for that apart or all along the rift zone for that distance. So individual lava flows only flow a few kilometers, but the eruption sites can be spread out over tens of kilometers. And
Nice.
the lava flows can be up to 150 meters thick. So they're quite. That's like 2/3 of the height of the Space Needle. So they're pretty big lava flows.
Nice. So a couple of questions about the magma chamber and the size. Do we know if that magma chamber size stays consistent?
We don't really know, but it's hard to imagine that it would change a lot over a short period of time. There have been seismic studies out at Axial Seamount. The most recent one was just in 2018. But those show that the magma reservoir is quite large. It underlies the whole caldera and even beyond. But there's the high melt areas are smaller than that, and mostly in the southern half of the caldera. So, we, except for these measurements of the earthquakes and how the seafloor is going up and down, we don't really have a way of directly seeing what's happening in the magma reservoir.
So this is kind of related. Is there a chance that that change in magma supply that you think you're seeing is related to the fact that the the pressure is being relieved somewhere else along the rift zone? And do we have a way of monitoring that?
That's a very good question. Because instead of the idea of it of this viscoelastic relaxation idea, another hypothesis could be that the magma is actually leaking into other reservoirs off to the side or moving around in some way. But that's conceptually possible, but we don't see any evidence of that. Our pressure measurements are now over a fairly big area, and we're doing repeat bathymetric surveys also, and we don't see any evidence of, for example, uplift off to the side where it's subsiding in the middle or something like that. So far we don't see any evidence of that.
And just a clarifying question, are the seismometer and the pressure sensors co-located?
They are not exactly, they're different instruments, so they're not exactly in the same place, but they're, the way the Cable Observatory works is there's nodes where you can plug instruments in. So there's 4 of these pressure instruments, there's 7 seismometers, so they're plugged into some of the same nodes. In some places they're close together, and some places they're not.
Okay. And then this takes us to thinking about terrestrial volcanoes. Can you tell us, is there a terrestrial volcano that's about the same size as Axial Seamount?
Well, so Axial's like 3,000 feet tall, so it's not huge. I mean, it's smaller than the Cascade volcanoes. So it would be, maybe something like Newberry volcano in the Cascades, southeast of Bend, something like that.
Okay. And David's going to take us on a deeper dive here. He is interested in asking about, has anybody analyzed the earthquakes that happened during the short deflation events? And is there anything different about their location or their mechanisms that you can talk about?
Good question. We've looked some at that. We've Jeff Beeson and I and Scott Nooner and William Wilcock and Suzanne Carbot have talked about this among ourselves. And yeah, we've looked at plots of the earthquakes before, during, and after these deflation events, and it's not super obvious that there's anything different going on there. It's mostly there's just fewer events. I think we have to look into that a little bit further to convince ourselves one way or the other, but my impression is it's the pattern, the spatial pattern of earthquakes, which I haven't shown today, doesn't really change.
Okay, wonderful. And that perfectly takes us to the end of our hour. So for everybody online, thank you so much for joining us. We appreciate you spending your Thursday afternoon with us. And Bill, it's every time I hear this story, it gets a little bit more in depth and a little more interesting, and I learn something new. So I thank you so much for your time, and thank you for sharing, and thank you for sticking with it and staying there and continuing to gather that information and sharing it with us. So thank you, everybody. Thanks to folks online, and hopefully we'll see you next week.
Okay, thanks.
You're getting a lot of thanks and congratulations and a wonderful talk, by the way. So it's all the clapping that you would normally hear, Bill. You just get, yep, clap, 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 I'm hearing. One might say explosive, so. Nice job. All right. Okay, everybody. Thank you so much. We'll see you next week. Thanks, Bill.
Hey, bye.